Let's look at another application of infinite series. So believe it or not, you've used geometric series your whole life. You may not have been aware of it, but every time you write down a number as a decimal, you're really using a geometric series, or at least a partial sum of a geometric series. So let's consider, for example, the number, well, let's go with pi, since we talked about it in the last video. Pi is 3.14159. But what does that mean? What are all those digits and the different places actually tell us? Well, if you think back to your elementary school days, we learned about the fact that we use kind of a decimal point as a reference point, and then the position relative to that decimal point tells us whether we're in the ones place, or the tens place, or the tenths place, or the hundredths place. And so 3 is in the ones place. The 0.1 is in the 1/10th place. The 4 is in the 100th place. The 1 there is in the 1000th place. And so this statement, pi is equal to 3.14159, or rather approximately equal to, is actually saying that this is equal to 3 times 1 plus 1 times 1/10th plus 4 times 100th plus 1 times 1000th plus 5 times 1 over 10,000 plus 9 times 1 over 100,000. And this number goes on forever, and so this sum would go on forever. And notice that's, well, it looks a lot like a geometric series, right? Now, it's not exactly a geometric series because the constant is not the same. It's different for each one. But it has a similar flavor because notice you could write this as, let's call the digit, let's call this a n. All right, and so this will be, maybe we'll call this a1, a2, a3, and so on. We can write this as the sum of digit an from 1 to infinity times 1/10 raised to the n minus 1 power, where 1/10 to the 0th power is 1, 1/10 to the 1 is 1/10, 1/10 squared is 1 over 100, and so on. Okay, so it is an infinite series, and it's very much like a geometric series, and you could certainly compare it to a geometric series if you wanted to talk about things like convergence. So actually, when we use number systems, we're using infinite series. It just so happens that many of the terms in those infinite series are actually 0. Okay, and that brings us to some interesting things that you can do with number systems. For example, you may have seen this before, but the claim is that the number 0.99999 repeating indefinitely is actually equal to 1. Not that it's close to 1, but it's actually equal to 1. And we can prove that by using this sort of series representation. Because what is 0.999? It is 9 times a tenth plus 9 times 100th plus 9 times 1,000th, and so on, which we could write down as a summation. It is the sum of 9 times 1/10 raised to the n, and we just need to start with n equals 1 here and go off to infinity, which looks like a geometric series. And if we shift our indices, we can actually use our summation formula to finish it off. So this is the sum from 0 to infinity of 9 times 1/10 to the, if we want to start with an exponent of 1, we need to put an n plus 1 there. And so we could write that as the sum of n equals 0 to infinity of 1/10 to the n times, I'll pull out one factor of 1/10 and we'll be left with a 9/10 out front. And so that is a geometric series with a constant 9/10 and the ratio 1. And so this has got to be equal to 9/10 over 1 minus the r, and the r is 1/10. Well, what's 1 minus 1/10? It's 9/10. And so that summation converges to exactly 1. Okay? So interesting, 0.999999 converges to 1, and other repeating decimals, you can use the geometric series formula to figure out exactly what they would converge to. So here's another one. 0.27272727, repeating forever. How could we write that as a nice fraction? Well, notice that's just 27 100ths plus 27 10,000ths. So I'm grouping into pairs of digits, plus 27, add 2 more zeros, 1 0 0 0 0, and then 2 more. So those are millionths, and that goes on forever. And so we could write that as 27 over 100 times 1 plus 1 over 100 plus 1 over 100 squared plus 1 over 100 cubed, which is going to be a geometric series, 27 over 100 times 1 over 100 to the n, and it converges to the c, which is 27 over 100 over 1 minus 1 over 100, which would be 27 hundredths all over 99 100ths. We can cancel out the hundredths, and both 27 and 99 are divisible by 3, and so we could write that as 9 over 33, or 3 over 11. And so there we go. 3/11 is 0.27272727. Okay, so our very number system is based around infinite series, believe it or not. And in fact, other number systems, like the ones that computers use, are also based on series. So for example, when a computer represents a number, it uses ones and zeros. And so if it gives you the number 1, 0, 1, 1, 0, 1.0101, it assigns places that are based not on powers of 10 or 1/10, but rather powers of 2 and or 1/2. So we can think of this as the 2 to the 0th place. This is the 2 to the 1's place. This is the 2 to the 2nd place. This is 2 to the 3rd, 2 to the 4th, and 2 to the 5th. And on the other side, we have the 2 to the -1 place, the 2 to the -2 place, and so on. So that number there can be written as 1 times 2 to the 5th plus 0 times 2 to the 4th plus 1 times 2 to the 3rd, and so on. And if we were to add up all of those numbers, we could convert back and forth between binary representation, which is how computers, again, represent numbers, and base 10 representation, which is how you learned to represent numbers in school. And so we can think about representing numbers using some sort of infinite series. In this case, it's not quite geometric because the numbers are all different, but you could also talk about something like the number, what is the number 0.11111111, repeating. If this is the 2 to the -1 place, and that's the 2 to the -2 place, and so on, then this just must be equal to 1 times 2 to the -1 plus 1 times 2 to the -2 plus 1 times 2 to the -3, and so on. And that one is actually a geometric series because the constant is the same. And what would that be equal to? Well, 2 to the -1 is 1/2. And so we'll have a 1/2 plus, and I'm going to factor out that 1. Next we'll have a 2 to the -2, that's a 1/4, or a 1 over 2 squared. The next one will be a 1 over 2 cubed. And that will continue. And we can even factor out a 1/2 there. And write this as 1/2 times 1 plus a half squared plus a half cubed, and so on. And so now we've got a nice looking geometric series. We've got our constant, and we've got our ratio is 1. And so this is just going to be 1/2 over 1 minus 1/2, which is equal to 1. So in binary, using ones and zeros to represent numbers, you can show that 0.11111111 is actually equal to 1, just like 0.99999 repeating is equal to 1 in base 10. Okay? So understanding geometric series and other infinite series is a very useful thing when you're dealing with number systems, in particular when you're trying to relate how we represent numbers to how computers actually represent numbers and store them in their memory.